Hello everybody, welcome to today's lecture. So today we're going to talk about chapter 4. This is another chapter, we don't, like chapter 1, where we don't really need to go into all of the details of it. We just need to know the overall general idea of it. So I'm going to kind of combine all of chapter 4 into this one lecture. And then we'll do the same thing with chapter 5 on the next lecture. We'll probably actually include some of 6 into the chapter 5 lecture as well. So that's kind of the game plan right now. So this is more probability stuff. So we're still focused on the probability before we get back into the statistics. Basically chapter 4, 5, 6, and even a little bit of 7 are cleaning up some of the probability that we need. And then in chapter 8, we're going to start really hard on the statistics. Okay. So chapter 4 is about what is called discrete random variables. Okay. So let's define some of these words first. Okay. So a random variable which I might often abbreviate RV if we write it a lot, describes the outcomes of a statistical experiment. Okay. So there's not really much difference between this definition and the definition of like a variable. The only real difference is that word random, right? It means that it's random. So it's relating to something like with a probability. Okay, so it's just like a normal variable, except there's some element of randomness to it. We usually write the capital letters to represent a random variable. We were just using them before as a variable, but from this point on, most of the variables we're going to look at are going to be random variables. Whereas if we use a lowercase letter, that usually denotes the values of a random variable. Okay, so the big letter is the variable itself. The little ones are the actual values, like our data. Okay. What does the word discrete mean? Well, discrete essentially means that like you can count. Okay, it means that you can count the number of outcomes. So like, for example, if we flip a coin and we get heads or we get tails, there's 2 possible outcomes. There's a countable number of outcomes, right? We can count them. There's 1 or 2. The opposite of discrete is what's called continuous. Continuous means that there's an uncountable number of outcomes, meaning it would be something like time in seconds, for example. Like if we measure how long something takes, the reason there's really an uncountable number of outcomes in that case is because if we really allowed as many decimal places as possible, it every time we like stop our stopwatch or whatever, whenever we do that, like with a regular stopwatch, we're really rounding, right? Because we can have like an infinite number of decimal places for those seconds. Like we could have 35.62318 seconds, or we could have 35.620000 seconds, right? We hardly ever are going to have exactly 35 seconds. We just round to 35 seconds, right? If we're like doing the stopwatch on our phone or something, just rounds to like the number of seconds. But we could be way more precise with it. So in reality, there's an uncountable number of outcomes. So that is continuous is when we have an uncountable number of outcomes, meaning like there's infinite decimals. And discrete means we can count the number of outcomes. Like there's 1, there's 10, there's a million, right? But we can count them. Even if there's a lot, it's possible to count them. Okay. The thing with continuous random variables, let me actually look at here. Let me write first the definition of discrete. Discrete means countable. Okay. So we can count them. So if we had a graph of a discrete random variable, it would maybe look something like this. Okay. There would be a bunch of dots. Okay. Something like this. Like maybe it's like the number of dogs that you own. And you ask a bunch of students, how many dogs do you own? And it's like 1, 2, 7, 0, 0, 4, etc. Right? They're all just numbers that we can count. And when we graph them, it would just look like a bunch of dots. Whereas if a random variable is continuous, it would look something more like this. Okay, it would be a continuous line with no breaks in it. Meaning that at any specific point, there's going to be a value. Okay. So this would be things like time, length, weight, height, anything that we measure, really. And this would be something that it's like the number of something. Okay. So continuous means that there's an uncountable number of outcomes. Discrete means there's a countable number of outcomes. Some things we should say, like with continuous, a lot of the times to really study continuous random variables, you need the tools of calculus. Calculus teaches you how to find like areas underneath the curves. Okay. Which we can't do with just like algebra. So a lot of the stuff we're going to talk about with continuous random variables is going to be more like approximate stuff, since we don't have that calculus tool. But with discrete, we can look at it a little more in depth. Okay. Let's look at what's called a discrete probability distribution function. Okay. A probability distribution function. Okay. Or a PDF. Okay, so often just use the abbreviation PDF. So the book calls it a discrete probability distribution function. A lot of books call discrete PDFs probability mass functions. So it would be mass instead of distribution, and then it would be PMF. A lot of books will call the discrete ones probability mass functions and continuous ones probability distribution functions. So here we're just using PDF for all of them, and then we're specifying whether it's discrete or continuous. Okay. By the way, if you want a better explanation of what the difference between discrete and continuous is, look in chapter 1. That's one of the sections we skipped, along with the qualitative versus quantitative. That goes into more detail with it. We just don't really need a lot more detail of it. We just need like a general understanding. Okay. So we're using the word function in the same way we would use college algebra, the word function, which we don't need to worry about too much, but it essentially just means that we have an input and we have an output, which is like with all probabilities. So I'll show you what I mean in a second here. But it has a PDF has two characteristics. Okay. 1, each probability is between 0 and 1. Okay, inclusive, meaning it can be 0 or 1. This really shouldn't even need to be said because all probabilities are between 0 and 1, right? So really the second characteristic is much more important, which is that the sum of the probabilities is 1. Okay, the sum of the probabilities is 1. This is what makes the PDF so important. If the sum of the probabilities is 1, that means that the PDF is telling you every possible outcome. So what the PDF is it's a function that shows you exactly everything that could happen and what the probability of everything happening is. Okay, so it shows you all of the possible outcomes and all of their possible probabilities. So, for example, let's look at here. Let's look at this example from the book here. I'll pull it up. I'll just copy and paste it. Here, let's go through this example in words, and then we can go through this one on our own, since this one's already written out in the book. So it says a child psychologist is interested in the number of times a newborn baby's crying wakes its mother after midnight. For a random sample of 50 mothers, the following information was obtained. Let X, the random variable, be the number of times per week a newborn baby's crying wakes its mother after midnight. So we could have 0, 1, 2, 3, 4, 5. So it could wake up the mother 0 times, 1 time, 2 times, up to 5 times. And then the P is the probability that we get that number. Okay. So when it says X equals 0, the probability that X is 0, meaning the probability that the baby wakes up the mother 0 times per week, which is what this is saying, the probability that X equals 0 is 2 out of 50. Okay. So about 4%. The probability that they wake them up 1 time per week is 11 out of 50. Okay. That would be about 22%. So the probability that they wake them up 2 times a week is 23 out of 50, 46%. So that's what this is saying here. It's saying the probability that X is this up to X is this 5 times. And 5 was the max. So these are all of the possibilities. And it's telling you the probabilities of all of them. And when you add them up, you get 1. Meaning if you turn these into percentages, this gives you 100% of the possible outcomes. Okay. So the function is exactly this column right here. Okay. So this is what a PDF would look like. So let's try our own problem with this one. Okay. And let me go ahead and increase the font size. Okay. All right. So it says Jeremiah has basketball practice 2 days a week. 90% of the time he attends both practices. 8% of the time he attends one practice. 2% of the time he does not attend either practice. What is X and what values does it take on? So X is our random variable. That's going to be like the thing that we want to know the outcome of. So in our case, we're going to want to let X be Just like with the baby example, right? With the baby example, X was the number of times per week a newborn baby's crying wakes its mother after midnight. In our case, we want X to be the number of basketball practices Jeremiah attends each week. Right? Once we have that established, the what the variable is, we can just write out our probability distribution function because everything else is given to us. We're told here that the probability that X equals 2 is 90%, which we write as a decimal as 0.90. Okay. Because 90% of the time he attends both practices. The probability that X equals 1, we're told is 8%, or 0.08. And the probability that X equals 0 is 2%, or 0.02. And you can see if we add up all of these, we end up getting 1, right? Or in percentages, it would be 100%. So this is our probability distribution function. So, I mean, it's really not anything like new. We're just kind of giving it a new name and using new notation. It's literally just writing out, like in math symbols, what all of the possible outcomes are and what the probabilities are. Okay. We were kind of doing a lot of this before. We just weren't necessarily writing it this way. We would write like the probability A or something. Like in chapter 3, we might have said, let A be the event that he goes to both practices. Let B be the event that he goes to 1. Let C be the event that he goes to 0, and written it that way instead of giving it a variable, giving the random variable a name and writing it with the equal signs. That's really the only difference here. Okay. Okay. So next, let's talk about expected value. Okay. The expected value of a well, the expected value in general is exactly what it sounds like. It's what value do you expect to get? So, for example, if I keep betting $5 on this card game and I do this 10 times, how much money do I expect to get at the end of it? And this is very useful because it makes us being able to calculate the expected value tells us whether or not something is worth our while, right? Like whether we should bother with it or not. So the expected value in general, the definition of it, the expected value is the long-term average, specifically the mean, okay? Because it is going to be weighted like a mean, not the median. So this means that over a long term, if we kept doing the experiment over and over again, this is the number that we would expect, okay? So, let's look at how we would calculate this. It talks a little bit about the law of large numbers, which I've mentioned before, but essentially what the law of large numbers says is that this long-term average, if you, it basically says like the more times you do an experiment, the closer the mean of your sample is going to be to the expected value, which is the long-term average. Okay. So, when we're dealing with randomness here, like when I was talking about betting, we can calculate the expected value, but that's not going to tell us exactly how much money we're going to win, right? Because we could get lucky, we could get unlucky. What the law of large numbers says is that if you do it for a long time, technically for an infinite amount of time, eventually you will hit that expected value. Okay. And it doesn't tell you anything about the short term. So oftentimes when we're doing this, we're thinking about what happens in the long term, theoretically. What happens in the short term is harder to predict, right? Because there's randomness to it. So that's what it's talking about here when it talks about the law of large numbers. By the way, the expected value is often denoted by the Greek letter mu because it's the mean. Okay. So it is quite literally the mean. It's not just like almost the mean or kind of the mean. It is the mean. So we use the same letter to represent it. It's just we typically use the word expected value when we're talking about probabilities instead. Okay. So to find the expected value, we multiply each value of the random variable by its probability and add them together. So we multiply each value of the random variable by its probability, and then we add them together. Okay. And by the way, the expected value, it's used for mu, but it's often also denoted like this, where we have E for expected value, and then in the brackets here, we write the random variable that we're looking for. And you could write it out in words too, but it would be written as E of X. I haven't seen that notation in the book, at least in the first few sections. I don't think. Maybe it was in there. They usually are just writing out mu or writing expected value in words, but most books will use this notation. Sorry, I keep thinking it's going to highlight, but it just makes a line. So let's look at how this works in practice. Okay, let's go back to this example right here. How would we calculate the expected value, or E of X? Well, it says to multiply the values by the probabilities. These are the values, the 2, 1, and 0. These are the probabilities. And then it says to add them together. So we do 0.9 times 2, right? The probability times the value, plus 0.08 times 1, plus 0.02 times 0. And this will give us the expected value. 0.9 times 2 is 0.18. Let me make sure we get all these right. Sorry, 0.9 times 2 is 1.8, not 0.18. 0.08 times 1 is just 0.08. 0.02 times 0 is 0. So we're going to end up getting 1.88. So what does this tell us in this context? This means over a long period of time, on average, Jeremiah will attend 1.88 practices per week. Okay. Now, obviously, this doesn't make sense in the short term because you can't attend a decimal number of practices. So this is just giving us a long-term average. If we look at all the practices he attends on the long term, assuming these probabilities are true, this is what it would come out to. Okay. Which makes sense because there's the greatest chance that he attends both of them, so it should be pretty close to 2. Let's look at the mother example with the newborn. Let me get that over from here. So let's copy this chart. Fix it here. Okay. So we want to take the values and multiply them by the probabilities. Oh, these aren't right. These are supposed to be fractions. Shoot. Okay. Let me see if I can paste it in a different way. Copy that. It really doesn't want to let me. There we go. Keep text only. Nope. All right. Let me do it as a picture. Oh, okay. That's fine. Let's just do it right from here. Okay. I'll just flip back and forth. All right. So we have the probabilities and the values. Again, these are the values, the 0, 1, 2, 3, 4, and 5, and these are the probabilities. So if we're looking for the long-term average of how many times the newborn baby wakes the mother, okay. So first we do 0 times 2 over 50. So here's our expected value, or you can write mu, doesn't matter. 0 times 2 over 50 plus 1 times 11 over 50. Okay, this was the probability that it's 1 time. Plus 2 times 23 over 50. Plus 3 times 9 over 50. And then it was 4 times 4 over 50. Plus 5 times 1 over 50. Okay. All right, so let's you can just do this in your calculator. First one is 0. You have 11 over 50 plus 2 times 23 over 50 plus that's going to be 27 over 50 plus 16 over 50 if you just multiply the numerators, plus 5 divided by 50. You're going to end up getting 2.1. Okay. So the long-term average is that the crying newborn wakes the mother up on average 2.1 times per week. Okay. So this makes sense with our probabilities because, again, 2 was the most common. There was about a 46% chance. And then the next most common one was the one right above 2. So that makes sense why it's just a little bit above 2. Right. So we're taking the values, multiplying by the probabilities. Okay. There's a lot more examples in the book here. It gives some notation, which you don't really need to worry about too much, but I'll just explain it. It gives this notation, okay, which is fine. It's saying Remember, this symbol right here, the capital sigma, means add them together. This is saying the data value times the probability of that data value. Okay. So add together all the data values times the probabilities of the data values, which is what we were doing here. Okay. It also gives a formula for the standard deviation of the PDF. Give me one moment here. Okay. So it also gives a formula for the standard deviation. Weirdly enough, the standard deviation is sometimes represented with a capital sigma, which is kind of weird because we use this capital sigma. It notes that, but then it also uses a lowercase sigma. So we'll just stick with the lowercase one. You really don't need to worry about this formula. I'm just writing it here because it's also in the book. Okay, so it is essentially taking your data values, subtracting off the expected value, squaring it, then multiplying by the probability, then adding them together, and then taking the square root. Okay, so like I said, I'm not going to ask you to calculate this. This is it's the standard deviation of the PDF. So it's like the long-term average distance away from the center, away from the mean. So oftentimes when we're talking about PDFs, we actually talk about the variance more than the standard deviation. So this thing squared. So same thing, except not the square root. Again, though, you won't need to calculate it. It's usually given to you. And what's actually nice is that what we're going to talk about next is the different types of distributions, and they usually have a like well-known PDF and a well-known expected value and variance. So we just can remember it from those rather than calculating it every time. Okay. So now that we've looked at a few examples, let's look at some of the common distributions. Okay. And we're not going to go really in depth with these. We're just going to kind of look at basically what they are. Okay. First is what's called the binomial distribution. Okay. The binomial distribution is a very common type of distribution where there are a fixed number of trials and there's two possible outcomes. You either succeed or you fail. Okay. So, we use the letter P to denote the probability of a successful trial. Okay. And we let there be n trials. So let n be the number of trials. So we're using n just like how we use it with the sample size because it's basically the same thing. Okay. This is just like our sample size. Let P be the probability of success, meaning that whatever we're seeing if it happens, it happens, right? So if we're seeing how many heads we get when we flip a coin, P would be the probability that we do get a heads, or 1/2. And then we let 1 minus P, which we usually write as Q, be the probability of failure. Okay. So it's 1 minus p because, remember, this is like the complement probability. If the probability of succeeding is p, then 1 minus that would be the probability of failure. But because the formulas look nicer, if we write q instead, we write q. Okay, but q and 1 minus p are the same thing. So if we know p is 0.4, then we know q is 0.6 because it's 1 minus 0.4. Another key thing is that the n trials are independent. So remember that word independent means that they have nothing to do with each other. So whether you get a probability on one of them doesn't affect whether you get a probability, or whether you get a success on one of them doesn't affect on whether you get a success on the next one. Okay. They're independent and repeated identically. Okay. So there's not going to be any variations between each one. I mean, the best example of this is just thinking of flipping a coin several times, right? Like you're doing the exact same thing every time, and none of them have any effect on each other, and they are repeated identically, right? So your p would be 1/2, your q would also be 1/2. And by the way, these are the only two possible outcomes. You could either have p or you could have q. Okay. Then I just want to make sure I didn't leave out anything. Don't think I did. If all of this is true, okay, so if you have your n, I said trails. That should have been trials. If you have your n trials that are independent, repeated identically, you only have two possible outcomes, which is success or failure. If all of this is true, then it follows what's called a binomial distribution. The outcomes follow a binomial distribution. The way we write this would be x, our random variable, is distributed as, which is what this symbol is meaning, the tilde. B for binomial, n comma p. So we write x is distributed as a binomial with n trials and probability p. And you would replace these with whatever they are, right? So say flip a coin 10 times. Then x is distributed as a binomial with 10 trials and p is 1/2, right? Because that's, maybe we would need to say like record number of heads, right? So the probability of getting a heads would be 1/2, and then we have 10 trials. If n equals 1, if there's only one trial, so we flip a coin one time, and there's only, so you do something once and there's only two possible outcomes, either it happens or it doesn't, it's typically referred to as a Bernoulli Bernoulli trial, Bernoulli distribution, Bernoulli random variable, any of those. I'll just write trial because that's what the book rights. So we have our binomial distribution where we do something n times and there's only 2 outcomes. If we only do it once, it's typically called a Bernoulli trial, named after there was a few Bernoullis. There was like a family of mathematicians that all of them had different contributions to math and physics and chemistry. So you see their name kind of come up a lot in different contexts. So what's nice about the fact that if we can recognize something is a binomial distribution, then it's always going to have the same long-term average, the same expected value. So the expected value of a Bernoulli a binomial random variable is n times p. Okay. The number of trials times the probability that you have a success in the trials. So if we flip a coin 10 times, what's the long-term average of the number of heads we expect? It's going to be 10 times 1/2, which is 5, right? Makes perfect sense. The variance, like I said, we typically look at the variance and not the standard deviation, is going to be n times p times q. So here it would be 10 times 1/2 times 1/2. So it would be 10 divided by 4, which would be 2.5. Okay. That one's not going to be as important as the expected value is. So if it's Bernoulli, because n is always equal to 1, your expected value is just p. And here your variance would be just pq, p times q. Okay. Now, like I said, we're not going to go super in depth with this. I just kind of want to show you what these are. I'm not positive if Excel has anything to handle this. Let me take a look here. Yeah, here, binomial distribution. So you can write the number of successes in trials. So let's say we have 10 successes. Let's say we did 30 trials. The probability of success on each trial, let's say, is 0.5. And then whether you want a cumulative distribution is something we didn't talk about. Let's just say false. Let's see what it gives us. It gives us 0.0279. So what is this giving us? Not sure. What did the formula say? Returns the individual term binomial distribution probability. I'm really not sure what number this is. Yeah, I wasn't sure if there was going to be a thing for Excel, but you can see there is. I'm not really sure what this number is returning, like what the 0.027 is. So maybe I'll have to look into that, and I can talk about that next time. So let's look at maybe All right, we're already going pretty long here. I'm kind of rethinking. Maybe I should break this up into 2 lectures rather than piling it all on today. Let's do an example with the binomial, and then we'll stop there and we'll go through the rest of chapter 4 next time. Maybe start 5. Okay. Let's grab a nice example from the book here. A lot of these are just writing the function or just writing out the problem. So let me find one that's not like that. I think that's what they're mostly going to do though, because really to calculate a lot of these, like, so there is a PDF function that binomials always follow. I've just noticed that the book is leaving it out. I think that's because it uses a function that we haven't talked about called the choose function, and it talks about it uses factorials, so it's only showing you how to do them in a calculator. So maybe we won't worry about actually calculating them because, like I said, it's only showing you how to do it in a calculator here. Like you can see, this is what it's doing right here. Is it's just showing you how to do it in a TI-83 or 84 calculator. So we could do it probably using Excel or something, but I won't worry too much about that right now. We definitely will need to be using like Excel or something to do some of the later stuff like the confidence intervals and the hypothesis testing, which the book is going to always go to default to the calculator, I guess. So maybe I'll look at what that's doing in Excel and I'll show it to you guys next time. Let's just look at one of these examples so that we can think about it, how to write these out. Okay. So it says the trainer is teaching a dolphin to do tricks. The probability that the dolphin successfully performs the trick is 35%. So P is 0.35, and then Q is 0.65, which it tells us, but we don't even need to be told, right? Because it's just 1 minus 0.35. Probability that dolphin does not successfully perform the trick is 65%. So out of 20 attempts, so n equals 20, you want to find the probability that the dolphin succeeds 12 times. Okay, state the probability question mathematically. So it's not even asking you to calculate the probability, it's just asking you to state the question. So if we let x be the number of tricks performed successfully, then the question would be, what is the probability that x equals 12 given that x is a binomial random variable done 20 times with probability 0.35. Okay. This is how we would state the question mathematically. I think maybe this is something we could try in Excel, actually. And I'm sorry, I wasn't prepared to do it in Excel. I was not really thinking that, so I didn't look at it ahead of time. But we definitely should. So we'll go to the binomial distribution. So, okay, so we're looking for, so that's what it was returning before. I understand now. 12 is this number. We're looking for what is the number of successes, okay? And it's going to return the probability. So there's 20 trials. The probability is 0.35. Whether it's cumulative or not, this is asking us whether we want to use what's called the cumulative distribution function or the probability distribution function. It actually says probability mass function. Like I was saying, the discrete ones are typically called. We're using probability mass functions only. We're not using the CDFs, the cumulative distribution functions. So we're going to put false here. Okay. And it's going to return this 0.013564. And that's actually the answer. So the answer is 1.35%. Okay. So we would need a calculator to answer something like this. This isn't something that we would be prepared to do by hand. There is a formula for doing it by hand. It's just not a very nice formula. Um, it is pretty tedious to do. So this is the best way to do it. It's more tedious than the standard deviation formula. So here's how we could do it in Excel. If you do have a graphing calculator, that's great. You're not required to. So, but if you do, you can go through this and look at how to do them. It has built-in functions, binom PDF, binom CDF. The the CDF is if we had a third column on the PDF where we added all the previous ones. So the first one would still be 2 over 50, but the next one would be 13 over 50 because it would be these two added together. And then the next one would be 36 over 50 because it would be the 13 plus the 23 and so on. So it's just two different things, but you can use either one. So that's why Excel is using, we have to say false at the end. If you use true, it defaults to cumulative. Okay. Okay. I think we'll stop there for today because, like I said, we're going pretty long here. Let me know if you have any questions, and we'll look at the other types of distributions next time, as well as some examples. And then we'll get into the continuous random variables. Like I said, we can't talk a lot about continuous random variables, so we'll just look briefly at them because you really need calculus to go deep in them. But then after that, yeah, we don't have too much more probability to do, almost into the more statistical part of this. So thank you for watching today, and I'll see you guys next time.